We're looking at a definition that puts a word to what we did in the last series of videos. The definite integral of f from a to b is signified by this kind of elongated s symbol. Out loud, this is the integral of f of x dx from a to b. And it's equal to the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I times delta x. This part here is what's known as a Riemann sum, although we won't refer to that very much at all, if at all. Delta x is b minus a over n, so the a and the b come from here. We take that interval and chop it up into n subintervals, and then the limit as n goes to infinity, of course. X sub I is a plus I times delta x. We have this definite integral provided the limit exists, and if it does exist, we say that f is integrable on AB, like differentiable, integrable. This might remind you of a definition you saw in the previous set of videos, where we said that the area of a region was the limit of, look, it's the sum of f of x sub I times delta x. Same thing, except we're not worried about whether it's a right endpoint or a left endpoint giving us the function height. F of x sub I is just some element in the ith subinterval. I'll say, though, that when we were looking at this in terms of area, this assumes that f of x is positive on the interval from a to b. F of x doesn't always have to be positive, and if it ever goes negative, it's just not an area. What does it mean then? Well, keep watching videos and we'll explore that as we go. Let's put this definition into action. We're going to evaluate the definite integral from 1 to 4 of x squared minus 4x plus 2 dx. And we're going to do so using this limit definition. And we're going to start out with, let's say, delta x. Well, actually, let's start out with a in this case and b in this case. It would probably make more sense for me to put it as a here and b here, because a is what we call our lower limit of integration, in this case 1, and b is our upper limit of integration, and in this case b is 4. They're also the endpoints of the interval over which we are integrating. Now, delta x being b minus a over n, in this case, is equal to 4 minus 1 over n, and so 3n. Excuse me, 3 over n. X sub I is equal to a plus I times delta x, and so 1 plus I times 3 over n. This is what we're going to use to replace x in our function x squared minus 4x plus 2, because we're looking at f of x sub I times delta x. So we've got the limit as n approaches infinity of the sum as I goes from 1 to n of, well, let me do this, x squared, and so 1 plus I times 3 over n squared minus 4x, and so minus 4 times 1 plus I times 3 over n plus 2 times, there's a delta x, right? This is dx, but in the definition it was delta x, and that's going to be 3 over n. You may wonder, when does delta x become dx? Well, when we take the limit, of course. Just like delta x over delta y becomes, no, just like delta y over delta x becomes dy dx when we take the limit when we're finding a derivative. Now, as far as the sigma is concerned, I is going from 1 to n. I is the variable, n is constant. Therefore, 3 over n I can pull in front of the sigma. N is not constant for the limit as n goes to infinity, right? N is the thing going to infinity. So I can pull it in front of the sigma, but not in front of the limit. And then if we simplify what's inside the parentheses, we end up with the limit as n goes to infinity of 3 over n times the sum as I goes from 1 to n of 9n squared 9 over n squared I squared plus 6 over n times I minus 1. You'll notice when I combined like terms, I did so in terms of I. As it turns out, n followed suit. Now there are properties of sigma notation. I won't go into them in detail right now, but suffice it to say that because a sigma is a sum, and we can rearrange and regroup the terms of a sum, I can rewrite the sigma breaking up the terms. I end up with the limit as n approaches infinity of 3 over n times the sum of 9 over n squared I squared minus the sum as I goes from 1 to n of 6 over n times I minus the sum as I goes from 1 to n of 1. Now for what's about to happen, it's going to be easier if I take the constant. Now again, n is constant, right, for the sigma. The only thing changing in the sigma is I. It will be easier for us if we take the 9 over n squared, pull it out front of that sigma, 6 over n, pull it out in front of that sigma. Now we have these three sigma expressions. One is the sum as I goes from 1 to n of I squared. One is the sum as I goes from 1 to n of I. And the third is the sum as I goes from 1 to n of 1. At this point, it would be good to remind ourselves of some summation formulas. The sum as I goes from 1 to n of a constant is n times that constant. As I goes from 1 to n, the sum as I goes from 1 to n of I is equal to n times n plus 1 over 2. The sum as I goes from 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. If the sum end is I cubed as I goes from 1 to n, then the result is n times n plus 1 over 2, the quantity squared. It's the square of what happens when you add a bunch of i's together. These are generally presented in a pre-calculus class. What we have are formulas for how to handle the sum as I goes from 1 to n of 1, and then as I goes from 1 to n of I, and as I goes from 1 to n, the sum of I squared. We aren't using I cubed in this particular case, but you probably will in the homework. So the sum as I goes from 1 to n of I squared gets replaced by n times n plus 1 times 2n plus 1 over 6. The sum as I goes from 1 to n of I gets replaced by n times n plus 1 over 2. And in the case I goes from 1 to n of 1, 1 is playing the role of c. C times n means that I have simply an n. They all had coefficients, 9 over n squared for the first one, negative 6 over n for the second one, and then a negative 1 essentially for the third one. And all of this is still being multiplied by 3 over n, and we still haven't taken the limit as n approaches infinity. What you will see is that there's, after distributing an equal number of factors of n in the denominator and the power of n in the numerator for each term. Here's what I mean. We get the limit as n approaches infinity of 27 over n cubed times n times n plus 1 times 2n plus 1 over 6 minus 18 over n squared times n plus 1 over 2 minus 3 over n times n is just 3. Now what comes to mind is limits at infinity, because we have n going to infinity here. Now in the numerator, if we were to multiply everything out, the biggest degree is 3. In the denominator, the degree is 3. All that matters is the constant coefficients of the factors of n, essentially. The first term becomes 54 over 6. The second term, I have 18 over 2. There's an n squared in the numerator, n squared in the denominator. As n goes to infinity, all that matters is the constants. So we have minus 9 there, and then minus 3 wasn't a surprise, right? 54 over 6 is like 9. So 9 minus 9 minus 3, the whole thing turns out to be negative 3. What does it mean that it's negative? I mean, nothing significant. It happens. I mean, ultimately, it means that we didn't find an area, really. But this is how we're going to use a limit definition to find a definite integral.